Cavemen and spectrometry. Cavemen and campfires. So, optical emission spectrometry, I've talked about it before in other shorts when it's a lifelong study for people. But anyway, this builds onto the spectrometry thing we need to get to understand isotope identification and how we do it and how we have been doing this for decades and what we know about it. But going back to optical emissions spectroscopy, or cavemen looking at campfires, the colors of light coming off the campfire have a very specific meaning. They tell you what's in the campfire, period, end, if you have an instrument that you can use to look at the campfire. That's optical emission, things that our eyes can see, spectrum of energy, photon energy, not electrical, not it's photons striking the back of your eyes. Photons have a frequency, that's the color that you see, and we call it light. So the cavemen sitting around a campfire invented film. We've taken a leap of knowledge here. So they've been staring at the campfire. They've been looking at the stars and the different colors of the stars and how they rotate and move, and notice the cyclical nature of the stars and create calendars. So looking at the campfire, somehow somebody finds a prism and notices they can create a rainbow from the sunlight. They can create a rainbow from burning things and using that prism. Then past that, someone created something called an optical grating, which is a flat surface etched with triangles. Well, one way of putting it. Looks like sawtooth maybe. And that mimics, does the exact same thing as a prism does. And all of this stuff you can look up, and an optical flat's kind of rare. If I had one, I'd love to show it and share, but hey. So, that looking at the light, we invented film. We have this thing called a prism or optical grating, because we've gotten more knowledge on this. And we take and stick the film on a wall in a room. And we let that prism, that optical grating, light shine on the film and expose it. And we precisely measure where we've placed the film in relation to the light coming onto that grating, onto that prism and back. And the light is all over the place. Those little lines, those spectrum lines of each color of light, each color, each frequency of a photon. We're talking in things called angstroms now amongst friends. But the library's being built. There's no computers. There's paper. You can write this down and make notes. But the physical library, the physical knowledge being built, are films of little straight lines down the film at very specific distances from, let's say, 0. And we can repeat these every time and measure them. And the different things we burn give off different lights. And when we can create higher purity materials, a lot of the light goes away and the light gets more specific. And you have these large film sheets to prove this. You can repeat this. The physics, the math is catching up to what we know we can do. The physics is still being invented, coincident. We're learning about quantums and reflections and waves. And we're still trying to stare at the stars and make calendars that fit our needs for commerce and trade. So these flat sheets in this business that makes these spectrometers, these film sheets, are in a book from the Vatican universities. These are the original references. The computer data, the models, the science, the math was built around what we saw visually. That's the power just of the photon to inform us of what's around us. So from that, this whole realm of spectroscopy, interferometry, the science, the math, the understanding of how that work comes. So inside this optical emission spectroscopy, we're now identifying atoms. Atoms from the periodic table, exactly and distinctly and discretely. We can measure them for ratios of one to the other. So beyond optical emission spectroscopy is mass spectroscopy. This is another machine that would sit coincident to an optical emission spectrometer. This machine identifies even better. It finds isotopes. The optical emission can find isotopes, but it's a little bit harder to do. But that scanning electron microscope, that time of flight spectrometry, how long it takes a particle to travel so far because of its weight. And more tables and more charts and more math is built around that, based upon coincident things we learned from studying light. We do this with pressure. So this is the measurement sciences. Now, where does this come into in nuclear talk? Well, we can detect nuclear decay because of the distinct particles it shows us with a different type of detector. But we're outside of the human realm pretty much. Our human sense to radiation is poisoning, is skin sloughing off, is huge amounts of mucus in the membranes trying to rinse and get this stuff out of your body. It's incidental cancer decades later. So different realm of measurement and how we do things. Inside of this, I mentioned isotopes. Isotopes are extensions of the elements in the periodic table. We know about these. We use them to date objects. We know the ratios. We've studied. We've made charts. It's on computers. It's in books on what these numbers, how we make and understand how things are put together. So this isotope dating, this radio isotope dating, this radio element, it is a huge part of science and how we know what we know. And we do these things. It's part of the proofs for dating rocks. It's part of the proofs for identifying basically the leftovers of genetic materials in other materials and being able to say it's genetic material when it's related to it. We're getting to 9 minutes. Spectroscopy in the world.